Okay. But yeah, okay, well, I'll tell you my final word then. Okay, so yes, thanks to the organizers for having me. So I would like to talk about spaces of smooth embeddings, right? So let M and N be smooth manifolds. Let's say of dimension little m and little n, respectively. So I want to talk about the space of embeddings of m into n. Actually, I will mostly talk about the case, mostly n is going to be a Euclidean space. New results such as they are only applied to this case, but we can begin in the more general setting. Right, so the starting point is going to be manifold calculus. So as probably many of you know, manifold calculus which was developed by Goodwin and Weiss, construct a sequence of approximation to this space. Or if you want a tower of approximations. So let me call it like EK embeddings, MN, EK minus 1, embedding, MN, etc. And this tower sits under the space of embeddings. And actually, it's not difficult to give an explicit definition of the case approximation. Let me remind you what it is. To define it, I define, I consider the poset of a certain poset of open subsets of M. So let OK of M be the poset of open subsets of M if you morph it to a disjoint union of copies of open balls or copies of Rm at most k. Okay, so disjoint unions of up to k open balls, all right, and then we can define Tk. The case approximation to the space of embeddings is the homotopy limit over this category embeddings of U into R. Right. And then restrictions to obviously OK minus 1 is a subcategory of OK. So the restriction maps give me maps on homotopy limits, and in this way I get a tower. Right, so first major result, one major result about all this, which makes it so interesting, is a conversion theorem due to Goodwin and Klein and Weiss. Which says that the map from the space of embeddings M into N to its case approximation is, I hope I remember it correctly, is k times n minus m minus 2 minus m plus 1 connected. Okay, so that tells me in particular that if n minus m is at least 3, the connectivity goes to infinity with k, and then the tower converges strongly. When the codimension is exactly 2, it still tells me something like, for example, when m equals 1, it still tells me that the map is 0 connected. So when m equals 1, we are looking at nodes or links, and then it tells me that the map is surjective on pi 0, which still holds.
Is it a homotopy limit?
Sorry?
Is it a homotopy limit?
Whole limit is homotopy limit, yes. Fair enough? Okay. Right. So let's ask ourselves, so what is this space of approximations? Can we understand in more concrete terms what it is? So you see the definition is involves homotopy limit, so it's a kind of homotopy theoretic nature, so maybe we can't expect it to be too geometric, but we can at least try to give some geometric meaning to it. And let me remind you a few things. So what is so for example, when k equals 1, so then we are looking at the homotopy limits over like the category of subsets which are homeomorphic to a ball, and it's not very difficult to convince yourself that this is equivalent to a space of sections of a certain bundle over M, where the fiber is a Stiefel manifold. And then identify the space of smooth inversions. So I guess mice using Smale-Hirsch theory. The first approximation is T1 embedding from M to N is homotopy equivalent to the space of smooth immersion from M to N. Strictly speaking, I have to assume that, at least assume that M is less than N. Or more generally, that the handle dimension of M is less than the dimension of N. So if M is okay, how about the second approximation? The second approximation is also a rather classical object, and I'm sure many people saw a discussion of it. For k equals 2, there is a homotopy Pullback square. Which describes the difference between T2 and T1. So T2 embedding M was to T1 embedding M. So this can be mapped to a homotopy fiber product. Let me try to describe it. The space of sigma 2 equivariant maps from the neighborhood of the diagonal in M minus M to F to M cross sigma 2 equivariant maps from F to M to F to N. And over maps, sigma 2 equivariant maps, the neighborhood of the diagonal to N cross N. Sorry. This is what I meant to write here is N cross N. Sigma 2 equivariant map from F to M to F to N. Let's see what does it mean. So first of all, FKN for any manifold is just the ordered configuration space, k tuple of distinct points in N. So in particular, F2 N is just N cross N minus the diagonal. Now, the neighborhood of, so what I mean by this, so inside M cross M, imagine the diagonal inclusion, right? And then imagine taking an open neighborhood of a diagonal, like a tubular neighborhood of the diagonal, and then the complement of M in the tubular neighborhood. Alternatively, if you want, you can think of this as the sphere of the tangent bundle. So this is the same thing as the sphere bundle of the tangent bundle over M. Okay? And so if you want, you can think of this space of maps as germs of maps defined near the diagonal. So let's see, how is this map defined? It's pretty straightforward. So imagine remember this can be identified with the space of immersion from M to N. So imagine taking an immersion from F from M to N, and take F cross F from M square to N square. Okay? So an immersion is locally injective. So when 2 points in M are very close to each other, then f of x1, then f matters with the same thing. So therefore, this is the space of pairs of points in M which are very, very close. And when they're very, very close, then f cross f maps them to distinct points in M. On the other hand, well, immersions are not injective, so M cross M will map to N cross N, and well, if I restrict it to just pairs of distinct points, this will map to N cross N. But when two pairs come together, then this map and this map near the diagonal, these two maps agree. So what I really mean by this is the homotopy pullback of the square. This is the homotopy pullback of the square maps, sigma 2 equivariant maps from F2M to F2N, sorry, to N cross N, going to maps sigma 2 M, let's say Fm minus 1, neighborhood of a diagonal, to N cross N, going to kind of maps sigma 2 M Fm minus 1 to F2N. All right, so this is a diagram. In fact, this map is a vibration, so you can even think of strip pullback square or homotopy pullback square. So what I mean by this is the pullback of this diagram. Okay. Yeah, the space of map which associates to a pair of points in M, a pair of points in N, which furthermore have the property that when the 2 points are together, then the points in R are actually distinct. So there is, I hope you agree, there is a natural map here. Now, if you have a map here, if an immersion is actually an embedding, then of course F cross F maps the complement of the diagonal to the complement of the diagonal, so then it would map here. So the homotopy pullback of this square is, one can show it is exactly the second approximation. So if we try to kind of imagine what this is really doing, so what does it tell us about the the T2. So a point in the second approximation space of embeddings of Mn consists of, well, an immersion of M into N together, and the sigma 2 equivariant map from F2M to F2N, right? Plus compatibility conditions. Namely, so first of all, one compatibility condition tells us that when 2 points come together, then F2 is really F1 cross F1. F2 is the same as F1 cross F1 near the diagonal. Okay, now earlier I said that this was a kind of a fibron pullback, so I could take either strict pullback or onto pullback. This map is not a vibration because the map from F to N cross N is not at all a vibration. So I really have to take a homotopy pullback. And therefore, so the second compatibility tells me that if I take F2 and I restrict it, I forget one of the points, I don't get F1, but I have a canonical path connecting me to F1. There is a path from F2 to F1 cross F1 in an appropriate metal space maps F2M N cross N, which is a constant near the diagonal. So,
what does constant near the diagonal mean?
what do we mean? So that for every, so I have F1 cross F1 is a map which is defined on N cross M.
Yeah.
If you take a point which is near the diagonal, right, so for every point away from the diagonal, there's a path from F2 of those two pairs of points to F1 of these points, and as it approaches the diagonal, they're the same, and it's a constant path. So the fact that I have to talk about paths here is a reflection of that I really want to take homotopy limit and not strict limit. So we get something less geometric, but we have more of a chance to analyze the homotopy type. Right. If you wish, we can simplify this slightly if we are willing to restrict ourselves to the case when n is Rn. Like so, if n is Rn, you may notice that then n cross n is contractible, and this whole part goes away. This whole is contractible. So let me simplify this now. So Rn. Max from sigma 2 m cross Sm minus 1 Rn cross Rn minus S. Right. So in fact, if you want, in this case, you can identify the pullback. So that now again, this map becomes a vibration, and homotopy pullback becomes a strict pullback. You can identify this pullback with what Michael Weiss called the space of strongly isovariant maps from n cross m to n cross n. Isovariant sigma 2 n cross m n Rn cross Rn. Okay, so these are maps which take the diagonal, sigma 2 equivariant map which take the diagonal to the diagonal, complement of the diagonal to complement of the diagonal, and moreover are injective on the normal bundle of the diagonal. or which is the same thing. So this is like f from n cross m to n cross m, such that the pre-image of the tangent bundle of n, of the diagonal n, is the tangent bundle of the diagonal. Okay, so you see, you can we got a simplification by trading restricting from a general n to Rn. Unfortunately, it won't work beyond the second stage. So somehow that particular simplification won't happen because it just so happens that Rn is contractible, but higher configuration spaces are not contractible. So you will see higher configuration spaces. Nevertheless, so I claim you can give a similar description of those higher approximations, which I will not try to give state precisely, but I try to give the idea, to give an idea. More generally, a point in Tk, the case approximation of the space of embedding from M to Rn is given by the following data. So first of all, I would have an immersion from M to Rn, and then a sigma 2 equivariant map from configuration space of 2 points in M, configuration points in 2 points in Rn, sigma 2 equivariant, all the way down to a map from Fk, k tuples of points in M to k tuples of points in Rn. Sigma k equivariant map. Okay, so I claim a point in Tk is given by a k tuple of maps like that, together with compatibility conditions, right? Plus compatibility conditions.
When you say conditions, it means data. Homotopies.
Sorry?
When you say conditions, that's including data, right?
I'm sorry?
Condition includes data also.
Data, yeah. Yeah, compatibility data. Okay, right. And yeah, I will try to get away with not trying to say precisely what they are, but roughly the points, there are two types of data. So one data says that if some points come very close together, then as 2 points, some points together, Fk approaches to the corresponding Fi, which is moreover, there is some normal bundle data, which is determined by the immersion F1. And right, so one of these, like, so one data is about regarding colliding points, and the other data tells me that if I take if I have a subset like of I, then the restriction of Fi to that subset is not the same as a lower subset, but there is a path between those. There are canonical paths from the thing. So for any St, let's say 1k, there is a path from Ft restricted to S, projected down to S, and Fs. Okay? Moreover, there are homotopies between compositions of paths. So if I have like a subset, another, in fact a third, I have two paths, and there is a homotopy between the composed paths, and then homotopies between homotopies, and so forth, plus compatible homotopies. So So roughly speaking, we can think of it this way. Let me try to say something. So imagine that we have an embedding from M to Rn.
Is this specific to having Rn
So-
as a target?
I'm sorry.
Is this specific to have Rn as a target here?
No, you can do it sometimes. It's slightly easier to state before. I think if I am no, this part you could write it for a general end. But let's just say it this way. So imagine that we have an embedding. So such an embedding would first of all.
You're giving you a little bit more space here.
You almost gave me a heart. So such an embedding is giving me an immersion. Rn, and of course an embedding will give me for every I a function from the configuration points of I tuples in M to I tuples in Rn, let's say, right? An embedding will give me such a function for every I. But if these functions come from a single embedding, of course, there are not going to be any, they're not going to be independent, they satisfy various compatibility conditions. So what I'm trying to say is that the space of the case approximation is the space of collections of functors which kind of satisfy the compatibility conditions which they would if they came from a single embedding in a kind of homotopy invariant way. But yeah, this is a lot of vague blah blah blah, so let me try to make a more precise statement. So what I want to say is that we can write the map from Tk to Tk-1 is induced from a canonical vibration, analogous to what we did for going from T1 to T2. So I'm now going to state a more precise make a more precise statement, and I hope that what I said so far will make it easier to believe the statement. So proposition for every k, there is a homotopy Hoover square. Tk embedding M Rn at sigma k covariant maps from a neighborhood of the fed diagonal in delta Km minus delta Km to Fkrn times maps, sigma k equivalent maps from the full configuration space Fkm to homotopy limit over the pole set of proper subset of a set with k elements F S Rn fiber product over the evidence space of sigma k covariant maps from neighborhood of the diagonal minus the diagonal to homotopy limit F S Rn. Okay.
What's delta K then? Is that at least
I'm sorry.
What is delta K of that?
Right. So inside M to the K, consider the so-called fat diagonal, right? So K tuples where at least 2 points are the same. Now imagine taking a small open neighborhood of the fat diagonal and take the complement. So think of this as a space of K tuples of points in M which are all distinct and where at least 2 of them are very close. Okay? So now imagine, so remember, this is the space of all, this has information about maps between I-tuple configurations of I-tuples of points in M to I-tuples of Rn, where I is less than K, right? But it also has like an immersion, a tangential data. So imagine that I have K points of which at least 2 are very close. So that's essentially like a small neighborhood of a smaller set of points. So this information, this space gives me enough information to construct a map from such a space into K tuples of points, the space of K tuple points in Rn, right? So given K points such that some of them are very close to each other, I'm looking at the function that I have them and I evaluate them at those points, and I have a way to do it to get a K tuple of distinct points in Rn, some of which are going to be very close to each other, but which are all going to be distinct. On the other hand, if I have K points in M, this
that only depends on the
this doesn't give me, yes.
that only depends on the immersion that is contained in TK-1 embedding space.
Well, the immersion determines what happens like when 2 points are very close to each other.
Okay, so
right?
only on the part where the
Yeah. But what do I have? So imagine that I have 3 points like this in M. So there is a function here which tells me that so I think of these 3 points as really being these 2 points together with some tangential data. And I know where these 2 points go, and I also know what should happen if I push away.
and
in a
if 3
certain
points
direction.
get close to one another, the compatibility precisely say it doesn't matter.
Exactly. Right. On the other hand, if I just have K points in M, I don't have a way to associate I don't have a way to associate an n tuple of points in N. But if I forget a sum, if I take a proper subset of a K point, then I have like I can evaluate it on the proper subset, and moreover I have all those compatible paths which tell me that I have a well-defined map to this homotopy limit over there, like this cubical diagram of configuration spaces over all proper subsets of the full set with K points. Okay. So if you think about it, so one thing this tells you is a result that is kind of probably familiar to many people here. So if you want to understand the homotopy fiber of the map from Tk to Tk minus 1, so what do I get here? I get the space of maps from configuration points in K and M, which are prescribed near the fat diagonal, into the homotopy fiber of the map from configuration space of K points to the homotopy limit of all the configuration spaces of fewer points, which is a well-known formula which was written by Michael Weiss. So this is a slight refinement of that formula, which tells you that you can pull it back you can pull back this vibration from this canonical vibration. Yes. So now, however, so all this is old and classical stuff, and also what I'm going to say next is pretty classical. But so now I want to try to use this to understand the difference between Tk and Tk minus 1, and moreover, maybe I'm interested today in figuring out some obstruction theory from lifting from Tk minus 1 to Tk. So let's again start from the beginning. Example. So let's look again at T2 embeddings from N to Rn, going to T1 embedding from M to Rn, going to maps from F to M, F to Rn, sigma 2 equivalent maps. Let me write it as the sphere bundle over M to F2 Rn. Okay, now F2Rn is a homotopy equivalent to Sn minus 1. So let me write it this as Sn minus 1. And I will use tilde to indicate that it has the antipodal action. Right? The complement of the diagonal is a sphere with antipodal action. Okay, right. So let us imagine that we have immersion, and I'm interested in knowing whether it's regularly homotopic to an embedding. Right? In other words, so the first attraction would be whether it is in the image or whether it's in the same component as in something in the image of T2. Right? Well, that's the same, that's if and only if its image here is in the image of something here. So I want some obstruction theory for understanding that. All right, so let us see. So let's say that we have a map from Sn minus 1 to Sn minus 1, a sigma 2 equivalent map. Well, we can always extend it. We can always write a commutative diagram like this. So given a map here will give me a commutative diagram like this, and it will give me a map from the homotopy cofiber of this map to the homotopy cofiber of this map. So I get a map from here to the space of sigma 2 equivalent maps from the homotopy cofiber of this. Well, this is a cofibration, so it's a cofiber. And this is really homeomorphic to just n cross n modulo diagonal to the suspension of Sn minus 1. Let me denote it as Sn hat. So it's just a notation that you do. So twiddle means antipodal action, and hat means the suspension of the antipodal action. So an action with two fixed points. Okay. Notations, right? So I get a natural map like this. And moreover, it is clearly, see, so if a map here comes from a map here, if a map here is a restriction of some map here, that tells me exactly that this map is null homotopic. And with a range, it's an if and only if. So they give me an obstruction for a point here to come from a map here. Moreover, I want a stable homotopy, theoretic abstraction. So this is now has a fixed point, and I'll map it to Q Sn. This is loop infinity sigma infinity of Sn. Sigma 2 is the variable. Lemma. So suppose M therefore equal I think n minus 2 right, then F map sigma 2 and Sn minus 1 Sn minus 1 is or extends to S2M up to homotopy. So in other words, it's a homotopic to a map to a homotopic to a map which is in the image of that restriction map, if and only if its image in map sigma 2 m cross m modulo n u f n is null homotopic. So this gives us an obstruction for lifting an immersion from T1 to T2. Now, of course, in a way, if you remember, the map from the space of embeddings from M to Rn into here, what was it? It is two. Find it now. Let's see if you write that formula, general formula. If you apply the general formula to the case k equals 2, this map is 2n minus 3m minus 3 connected, and this map is n minus 2m minus 1 connected. Right? So then it tells me that if this is at least 0, then an immersion within the range of dimensions, an immersion leads to an embedding, even only if it leads into T2, which is even only if it vanishes here. So assuming that this is if this is at 2n minus m minus 3m minus 3 is greater or equal to 0, so in other words, if m is less or equal to 2/3 n minus 1, I guess, then f an immersion to Rn if is regular homotopic to an embedding, even only if its image here, so let's call it image here, the obstruction bench. Now, of course, goes without saying, this is a very classical obstruction, and one can interpret it geometrically. I'm sorry?
The blackboard, the back blackboard, can you push it up?
The green board?
Yeah. Maybe you can't.
Okay. Right, yeah, I'm sorry, I went so down here. Okay, I'm sorry. Both my hearing aid batteries went out, and while strictly speaking, it's not necessary for me to hear what I'm saying. Maybe it will be better. So, excuse me for just 60 seconds. Right. So yeah, you can interpret this map as a kind of a framed cobordism in M. So this is a nice framed cobordism interpretation, and namely it is really the cobordism class of the double points. So a geometric interpretation so suppose F is an immersion so modify F so that F cross F from M cross M into Rn cross N is transverse to the diagonal. Okay, and so let us consider F cross F the preimage of the diagonal here. Now the preimage of the diagonal contains the diagonal here that I don't want. I want what it is minus the diagonal M is the double point set. And so this is going to be, this is a frame submanifold, a framed submanifold of M cross M minus M. And if F is regular homotopic to an embedding, then this should be frame cobordant in a suitable sense, frame null cobordant in a suitable sense. And then one can work out that this obstruction is equivalent to this null cobordism. Right, so yeah, again, this is all very classical stuff. So for example, like in this, so what the upshot is that pi 0 of this space is giving me obstructions for lifting from T1 to T2. Of course, pi 0 is especially nice if things are especially nice if pi 0 happens to be the lowest homotopy group. That happens if 2m equals exactly n. In that case, the obstruction is just a single point, and you get the Whitney obstruction, right? So this is also a way to kind of, you can see the Whitney's so-called, the Whitney abstraction to for an immersion of M into R2M to be regular homotopic to that entity. All right. So what happens usually with these towers is that if you do it, like when you look at the first two stages of the tower, you get something very classic. When you do like the third stage, you get something which is much less classic, and if you manage to push further, you have a chance to do something new. So yeah, this is goes back to, I guess, Haefliger. This is a formulation of Haefliger and Dux, and also all the way back to Whitney. Now let's see what happens if we try to understand liftings from T2 to T3. So this also has been studied. This was studied by Brian Munson. Let me try to tell. Next. Consider lifting so let's see how we're gonna write it. So we have T3 embedding for Rn, T2 embedding from M to Rn. Times I have to look at maps. Sigma 3 equivariant maps it was supposed to be the homotopy pullback of all restrictions over all proper subset of 3 points. But a proper subset of 3 points is only the only interesting cases are now the 2 points, because when I have 1 point or 0 point, I get contractible. So in this case, it slightly simplifies as to just F2V cross F2V cross F2V. Right, because the homotopy pullback is this, over whatever I have to put here, maps, sigma 3 from
V is Rn, right?
these
V
are.
is Rn, right?
Okay. So now I want to understand that, again, the goal is to write down some kind of map from here into something. So that would be a vibration sequence in some range, which would include, ideally would include pi 0 in something like this. And I will phrase it this way. So this is a result of Munson. I'll phrase it a little bit differently. There is a sigma 3 equivariant map from F2Rn cross F2Rn cross F2Rn to loop infinity sigma infinity S2n. Now remember, this has an action of sigma 3, so a sigma 3 acts, so think of S2 as having the standard action of sigma 3. So this is, yeah, right? And there is an initial map like that, so that if I compose it with the map which takes a triple of points and evaluate it in each 2, this is going to be null homotopy, the composite is null homotopic, and moreover, it's a vibration sequence in a certain range. So that we get a vibration sequence in a certain range. Okay, now let's see. If you think about it like from plausibility, you can kind of convince yourself of the plausibility if you think about homology, right? Because the homology of both of these spaces is concentrated in degrees which are multiples of n minus 1. So I have some homology in degree n minus 1, and then in degree 2n minus 2, and so forth. In degree n minus 1, the homology of these 2 point spaces is isomorphic, it's z plus z plus z. In degree n minus 2, this is famously have z plus z, while this is calculating z plus z plus z. So in fact, so in homology, the first difference is like a z in dimension 2n minus 2. And then by some kind of stable, so it's going to be a covibration sequence in stable range and also a vibration sequence in a stable range. So it's plausible. I want to give a particular, I want to try to describe this map from here to here. The map is described, so actually I want to describe a map from F2Rn cube to, I first want to look at non-unbased maps from a circle, so we map to S2n minus 1, and then, so given a map like that, I can take its unreduced suspension and get a map from loop 2 S2n, and then I can stabilize it, use S2n. So the map is actually going to be constructed on this level, and then I can just push it forward with standard stuff. How am I going to construct this map? So let's think of this space is as Rn cube minus the same diagonal Rn. So triples of points in Rn which are not all the same. And remember, I want to construct a map. So I want to construct a map here which somehow measures the failure of a point here to be in the image here. So what's the point here? A point here is a triple of pairs of numbers. So imagine a point here as being like a pair of points like x1, x2 in Rn, and then maybe y2, y3 in Rn. So now if these points come from some points a1, a2, a3, then I expect the third pairs to be essentially x1, y3, y3. But the third pair can be something different. So let's imagine the third pair is something 1, 2, 2, 3, v1, v3, right? So a point here is a triple of pairs of points in Rn, and I want a map which somehow measures the failure of the point to be in the image of the map which stands a1, a2, a3 to a1, a2, a1, a3, a2, a3. Okay? Right, so again, if they were, then somehow the third pair would be determined by these two. So what can I do with that? Right, so I want to associate to this data a triple of points in Rn which are not all the same. Now, I can translate things up to translation in Rn, things don't change. So for example, I can take these two pairs and gluing x2 to y2, I get pairs, a triple of points like x1, x2, y2, y3, right? So by taking these two pairs of points and translating them parallel so that's the point, I get a triple of points. Moreover, I know that this is different from this and this is different from this, and so certainly they're not all the same. So that's one way to associate with a point here, a point here. But then I can also take these 2 points and get take these 2 pairs and get something like x1, x2, z1, z3. So in this way I get a different triple of points, which is dictated by these 2 pairs, and a third triple of points, which is dictated by taking these 2 pairs, which would be something like y2, y3, z3, z1. So what I'm saying is, by taking these 3 pairs and by taking 2 at a time, I get 3 possible points here. But I can connect them, and so I can construct a loop there. So for example, if I take, if I consider, so this is the pair which is associated with this graph, this is the pair which is associated with this graph, and this is the pair which is associated with this graph. And if I compare these 2 pairs, like x1 and x2 are always the same, so I can take this point y3 and map it to z3. And since along the way these 2 points are gonna be taken separately, it's gonna be allowed. It's gonna be allowed. So in this way, I get, probably I didn't make a lot of sense, but in this case, you get a well-defined loop of these things. And the loop is parameterized exactly by this poset of certain graphs on the set with 3 elements. And this is what's called the poset of not one connected graph. All right, so that's what I claim is a general statement that we can make. So there are. Do I have 5 more minutes?
Is there a stoppage time? Stoppage time?
I'm sorry?
Yes.
Yeah, okay.
Before we get to penalty fix.
All right, so I claim, first of all, I say that so to complete Brian Munson's theorem is that, so first of all, so again, I say assuming that m is at most n minus 2, well, right, a point in T2 of embeddings is in the path component of the image of T3 if and only if Munson's obstruction vanishes. And then, since the map from the space of embeddings to T3 is so much connected, you get an improved range of dimensions. So if both Haefliger's obstruction and Munson's obstruction vanish, then an immersion leaves, in a certain range of dimensions, an immersion comes from an embedding if and only if the two obstructions vanish. Now, at this point, I should ask, okay, so is there a general pattern? So, like in both cases, we came up with some kind of infinite loop space which admitted a map from this space, which sort of was a federation sequence. But if you're going to extend it, it would be nice to have some general reason for such an infinite loop space exists. So that's one thing I want to say. I said the general reason comes from orthogonal calculus. So this is where orthogonal calculus can come into play. And for me, it was a very useful framework. Somehow told me that how to generalize it. Notice. The homotopy fiber maps from tk to tk minus 1 is roughly the space of maps from, let me write it as a map from tk, which are prescribed near the fed diagonal, tk m, to reduced configuration spaces of key points in Rn, where by reduced I mean the total homotopy fiber of the cubical diagram, which I get by looking at all possible subsets. Now think of it as a functor. This is now a functor of Rn. So one can apply orthogonal calculus. I don't have time to really tell you what it is. So it's more similar to Goodwillie homotopy calculus. It gives me a homotopy, it gives me a Tower conversion to it where the fibers are given by spectra with an action of orthogonal group. So I claim orthogonal calculus tells me the bottom non-trivial layer occurs in degree let's see, k minus 1. Okay, and it is given by the space of maps from the bottom not trivial layer, let's say, of the reduced configuration Rn is given by map from S2 vk sigma infinity S k minus 1 n. where dk is the complex of not one connected graph. Okay, right. So a graph is not a graph is one connected if it is connected and if it has the property that if you remove any one vertex, it's still connected. So, for example, this graph is connected, but it is not one connected, while this graph is one connected because if I remove any vertex, it's still one connected. So given a k, you can look, so what I have shown you earlier was exactly the complex of not one connected graphs. It is known that the complex of one connected graphs is dk is homotopy equivalent to a wedge of spheres of dimension 2k minus 3 of k minus 2 factorial spheres. So notice that this is a complex with an obvious action of the symmetric group, but it is homotopy equivalent to a wedge of k minus 2 factorial groups. It's of course realizing the Haefliger operator, which was right. And one can also identify it as a moduli space of unrooted trees. It's really the suspension. So you see, because of the dimension, it tells you that this is sigma k minus 1, I think. W stands now for Sarah Whitehouse. For Sarah Whitehouse, a space of trees. Okay? So what I'm claiming is two things. So first of all, so the principal part of the homotopy fiber of this map is determined by this moduli space of graphs. Moreover, if I write down this vibration sequence, if I take the homotopy fiber of this, it does not deloop. I cannot extend it to the right. But if I just take the principal part, the bottom non-trivial trail, that's an infinite loop space, and I claim there is a map, there is always a map from this space to the delooping of the principal part. And in this way, you get an obstruction, and you get a vibration sequence in a range, which kind of is enough to give you an obstruction. And I'm sorry I ran so much over time. Thank you.
Questions?
Showed us the interpretation of the first obstruction as a stable Wilson class. Is there also something like that for Munson's?
Yeah, well, not in full generality. So, for example, if you take a case when like M is a disjoint union of three pieces, and then you think of it more like obstructions of links between them. So then things are a bit easier because you don't have to think so much about what happened to points. Yeah, there is an interpretation, and it actually goes back to earlier work of Koshorky and also Munson as a kind of overcrossing, the overcrossing locus. I'm not going to try to describe it because I don't understand it well enough myself, but there is something like that. But that's one of the things I would like to do. I would like to write down. So one thing is, one obvious point to make is that this is of course not a manifold. It's a finite complex, so it's somehow not immediately clear how to interpret geometrically Borgian classes in it, but there ought to be something. Yeah.
Can you write down an immersion that lifts to T3 but not to T4?
That what?
That lifts to T3 but not to T4.
That lifts to T3 or not T4. I think so. Like for example, one good situation, one interesting case, like two-dimensional manifold inside R4. So that's one case where you have non-trivial obstructions in all degrees. And the answer is no, but I hope that I'm working on it, and I hope I will be able to do. I think yes, you should be able to.
All right.
Can you say something about immersions of two spheres and four manifolds?
Well, I not at this point, but I was going to say that, right, so one interesting case is when m is 2 and n is 4. And that's it. Yeah, that's one case where you have like non-trivial obstruction in every degree. And so of course, Teichner and Schneiderman, Teichner and collaborators wrote a lot of some papers about it. And at this point, all I can say, it looks like there ought to be connection. Like also another interesting case is when, of course, m is 1 and n is 3. So then you don't have obstructions, but then it's more, you have, then it gives you more like invariance. It parameterizes points in pi 0, and that's a familiar theme that this is closely related to Vasiliev invariance and also Milnor invariance of links. And on the other hand, Teichner wrote down some correspondence between Milnor invariance of links and his invariance of surfaces in R4. So my hope is that, yes, I'm still trying to figure it out. This is very much work in progress, but yeah, hopefully.
One more.
There is a notion of suspension of immersions, and
I'm sorry?
one can suspend immersions just by crossing with a copy of R. And,
Right.
and I think that there are some filtrations where you classify immersions by how many suspensions you need
Right.
to get them to embeddings.
Right.
Has this tower something to do with the
I
other
don't
one?
know. I mean, it's not a good question. I don't know at this point. Yeah.
Because it has something to do with cobordisms, I'm sure.
Right.